All right, so today we'll study electromagnetic induction. We'll learn how all electricity is produced currently. Okay, well, this law will show you how electricity is produced except for photovoltaic cells. Okay, how dams produce electricity, how nuclear power plants produce electricity, windmills, and all that. Okay, so what we are studying is this equation and this equation. So everything we say in this chapter is a result of these two equations. Okay, this is called the Lorentz force law, and this is Maxwell's Faraday's law. Okay, so again we learned that on the right hand side are the causes, and the left hand side are the effects. Okay? So what this is saying is, if you have a time varying magnetic field, it produces an electric field. Okay, so let's say you have a magnetic field like this. Okay, and what this equation is telling you is, now if you change this magnetic field with time, so make it stronger. Okay, so for instance, if magnetic field is increasing in this direction, what it does is it produces an electric field. This equation is telling you this. Okay, this magnetic field will produce an electric field like that. Okay, stick your right hand out. If the magnetic field points in the direction of your thumb, your fingers wrap around like that, the electric field is in the opposite direction. That's what that minus sign is. Okay? All right, so just looking at this equation, how long does this electric field live? I mean, just looking at that equation. This is non-zero as long as dB by dt is not zero. As long as the magnetic field is changing. Soon as the magnetic field stops changing, this electric field dies. Well, how far does this electric field go? Yeah, all the way to infinity. Well, what good does it do? You stick a wire there, and it'll produce a current in the wire. You can cook your pizza. You can toast your toaster. Okay. So, all right, so changing time varying magnetic fields are producing electric fields. Okay. And there's trillions of dollars invested in this. Okay. And that's what we're going to study. Do you guys understand? Okay, so now we'll see how to change the magnetic field. Can you think of a way to change this magnetic field? All right. So here, take a magnet like this and push the magnet back and forth like that. Okay, so all you need is a piece of wire there, a piece of wire here. You move the magnet back and forth, and you'll have a current in the wire. Okay, so here's a magnet. You move it back and forth, and you'll induce an electric field in this wire. You'll induce a current in this wire. No batteries. Sounds like you're creating electrical energy.
It's kind of how like the regenerative motors in cars work.
No. So what you're doing is you're converting mechanical energy into electrical energy. As soon as you stop moving this, you're not producing electrical energy anymore. Okay? All right. So did you guys understand that? So this is the equation we're studying. All right. All right, so you see when this is stationary, there's no current. When you move this back and forth, you have a current. Okay? And what is this showing you? What is this? Hmm? Yeah, when you pass a current through a solenoid, that's a magnet. So this is an electromagnet. So you move this electromagnet back and forth again, you have the same effect. What happened here? So here's a solenoid inside this other solenoid. When you close the switch, what happens? When you close the switch, a current starts flowing, and so momentarily its magnetic strength goes from 0 to maximum value. So magnetic field is changing, and so just for a flash, there is an induced current. Once the current is steady in this thing, there won't be any current. Okay. All right. Again, this is a very important chapter. You'll see a lot of applications using this law. Okay. So what we're studying is, one of the things we're studying is changing magnetic fields producing electric fields. Okay. And of course, electric fields are also produced by charges, but this electric field has a different nature to it. Okay? And we'll talk about that. Okay, so here's another situation. Okay, here's a solenoid, you're passing a current through it, and now if you change the current with time, this magnetic field changes with time, and that will induce an electric field all around it, and if you split a wire, you'll get a current through the wire. Okay. So this is the induced current. When will this stop? How do you stop this current?
When you stop moving.
Stop.
When the magnetic field stops moving.
When di by dt goes to 0. If the current in this solenoid is steady, you won't induce a current in the secondary coil. See, what you're doing is you're inducing a current in the secondary coil without any batteries. You're driving a current in this wire without any batteries. Okay? This changing magnetic field can induce this current. Okay? So in this chapter, we look at time-varying magnetic fields producing electric fields. Okay? All right, so in preparation for it, we'll define something called magnetic flux. You can think of magnetic flux as roughly the number of field lines threading an area. Okay, so magnetic flux. So if the field lines are perpendicular to the area, the magnetic flux is just the strength of the magnetic field times the area. Okay, so you can think of that as how many lines are threading this. How many lines are threading this area now? 0. So we define the flux as B dot area. Okay, the area vector is the vector points perpendicular to the area, and the magnitude of the area vector is, of course, the area of that surface. Okay. So with that definition, B dot A, when B and A are perpendicular, then that's 0. Okay. So that's magnetic flux. Okay, so here's Faraday's law. Okay, what Faraday's law says, the induced EMF is equal to minus d phi by dt. Phi is the magnetic flux, the subscript B telling you magnetic flux. The induced EMF, the negative sign is related to the direction. Okay, the negative sign is related to this thing that we said. So here is the magnetic field, and you can calculate the flux through this area. The negative sign tells you the direction of the induced electric field. Okay. So if the sign was positive, the electric field would have been in that direction. Okay. All right. So Okay, so Faraday's law says the induced EMF is minus d phi by dt. Okay. And of course, the magnetic flux is B dot. The magnetic flux is, you just saw, is B dot area, which is BA cosine theta, where theta is the angle between the B and the A vector. All right, so the induced EMF is d by dt of dB A cosine theta. Okay, now if we look at this, okay, so anytime you want to induce an EMF, all you need is this right-hand side to be non-zero. You want to produce a voltage, you want the right-hand side to be non-zero. How do you make the right-hand side non-zero?
Ensure that B and A are not related.
Okay, you could change B, you could change A, you could change theta, or you could change all three. You could increase the strength of the magnetic field or decrease the strength of the magnetic field as long as B is time dependent. Or you could hold B steady, change the area. Or you could do the following. You could hold B steady and change the angle by rotating the loop. Did you guys understand that? You don't understand this diagram? Okay. So what you're trying to do is you're trying to induce an EMF in the loop of wire, right? So to induce an EMF, you want this to be non-zero, the right-hand side to be non-zero. Well, you can have B constant, A constant, and just change the angle theta. Okay. So let me draw another diagram for you. So let's say this is B. I'm going to hold B constant and here's the area vector. This is B, there's theta. And the way I change theta is I rotate the loop. Okay? Did you guys understand that? All right, so to induce an EMF in the loop of wire, you could either change B, A, or cosine theta. And in practice, it turns out that that's the easiest thing to do, rotating the loop. Okay? So for instance, there, you have a permanent magnet, the magnetic field is constant, the area of the loop is constant, and all you do is spin the loop. And you produce electricity. And so whatever work you put in turning the loop is being converted to electrical energy. Did you guys understand that? How do you turn the loop?
A turbine.
Hmm?
A turbine. Gas motor.
So in a windmill, the wind is turning the blades, which is turning this loop of wire. In a dam, you release water. The water is turning this loop of wire. In a coal power plant, what do?
Steam is turning it.
Steam is turning it. You burn coal, from the heat released, you boil water, and the steam is turning it. In a nuclear power plant,
Steam is also turning it.
Yeah.
Boiling water.
you split nuclei, the hot products, you boil water, maybe, and the steam is turning. Yep. In a natural gas plant, you're also doing the same thing. All right, so now you understand how electricity is produced. Okay, solar panels work differently. So that's the idea. Okay, so you guys understand Faraday's law? Again, the induced EMF is time rate of change of flux. Okay? So again, you could change the magnetic field. That's hard to do. You could change the area, but that's not practical. The easiest thing to do is change the angle theta. Okay? And that's what you do in all generators. All right, any questions before we move on? Okay. All right, so in this thing, now the question is, when will the light, when will the bulb light up? So for instance, if you move the magnet here, what are you doing? When you move the magnet at the location of this wire, the loop of the wire, what you're changing is B. Okay? And you'll induce a current through this wire and the bulb will light up. If you move this, if you keep the magnet stationary and move the wire, this is the same thing as doing that. Okay? At the location of the wire, the magnetic field is changing and the bulb will light up. What are we doing here? This is stationary, that's stationary. You're increasing the area. In this case, you're increasing the area. B is constant. Okay? So the bulb will light up. This is the only case when the bulb won't light up. Okay? All right. So here's another puzzle. What does this current do? Very good. It produces a magnetic field. And the magnetic field it produces are like this, are concentric circles. Okay? And the further out you are, the weaker the magnetic field. Okay? So the magnetic flux is the number of magnetic field lines threading this loop. And now that just depends on this distance. And as long as this distance is not changing, if it moves parallel to the wire, the flux will not change. The flux will not change. And there is no current induced in this loop. When it moves in any direction but parallel to the current, flux is induced. Flux changes and current is induced. This is the direction in which the induced current is the maximum. Okay. All right, so here's Faraday's law again. What does it say? The induced EMF is negative of the time rate of change of magnetic flux. Okay. What is magnetic flux again? The number of magnetic field lines threading an area. Okay. All right, now we'll tell you what this negative sign means. Okay, it's related to Stokes' theorem, but we'll give you a simple answer here, a simple thing to remember. Okay. So what we just learned was if you move this magnet relative to the loop, a current is induced. Again, let me emphasize, here's a current in this loop of wire with no batteries. How long does this current last? As long as this magnet is moving. As soon as the magnet stops, that current stops. Okay. You want that current to keep flowing, you have to keep moving the magnet. Okay. And again, like we saw in the generator, it's hard to keep the magnet moving, so instead what's easier to do is to turn the loop. Okay. And you induce an electric current. You induce a AC voltage in the loop of wire, and that depends on the way it's connected. if this loop of wire were connected like this, okay, you would generate a DC voltage. Okay. But we won't worry about that. In all our applications, we generate AC voltage. All right, so going back to, where were you? Okay, so we were trying to figure out this sign. Okay, so you saw that when you move the magnet, there's a current induced. Now what we want to know is, what is the direction of this current? Okay, so when you move it toward the loop, the current is induced like that, counterclockwise, and then when the magnet moves away, the current is in this direction. Okay, so the question is, how do we remember this? How do we figure this out? And Lenz's law tells you that. Okay, so here's the deal. Okay, so when you move this magnet, a current is induced. The induced current lasts only as long as this guy is moving. Okay. All right, when a current is flowing through this guy, what is it acting like? What does this become? It's become an electromagnet. Okay, and what do? You use your right hand, point your fingers in the direction of the current, and your thumb points in the direction of the magnet. So while this guy was moving in this direction, this guy became a magnet with the north pole pointing in that direction. And what is the induced current doing? It's opposing this motion. Okay? So the induced current, it's like biting the hand that's feeding it. Okay? So the induced current is opposing the change that is producing it. And that's what Lenz's law says. Okay? So for instance, when this guy is trying to move away, the induced current is like that, so the induced current is like that. And this is a south pole, and it's telling the magnet, hey, don't go away. Okay, so that's this Lenz's law, which is related to that negative sign, gives you the direction of the current. Okay, so physical interpretation of the negative sign is given by the next Lenz's law. Polarity of the induced EMF is such that it opposes the change in flux that produces it. Okay. So if the flux is increasing in this direction, the induced EMF will try and decrease the flux. All right, so we looked at the Faraday's law encompasses everything. It encompasses everything. But so first we looked at time-varying magnetic fields producing that EMF. Now we'll look at a second aspect of it. We'll look at motional EMF. Okay, so what this tells you is the following. Here's what the diagram is showing you. What are these crosses telling you?
It's going into the page.
Yeah, so there's a magnetic field into the page. And what you can do is take a metal rod and move perpendicular to the magnetic field. You take a metal rod and move perpendicular to the magnetic field, and what happens is, since this metal has free charges, the electrons will collect at the bottom, and this end will become positively charged. So now this is acting like a battery. Okay, there's a voltage induced. That's why it's called motional EMF. Okay, so this will act like a battery, and in fact, it's a real battery. You can drive a current through your load. Okay? So if you put this rod on a rail and you make an electrical connection, you can toast your bread, you can wash your clothes, you can do whatever you want with that current. Okay? And, oops. Okay. And how much is the voltage across it? The voltage is B, the strength of the magnetic field. This is when the when the rod is moving perpendicular to the magnetic field. Okay, it's B, the strength of the magnetic field, L, the length of the rod that is in the magnetic field, times the velocity. So the voltage is B times L times V. Okay, and you can see that the faster you move the rod, greater the voltage, stronger the magnetic field, greater the voltage, and so on. Now, if you move the rod parallel to the magnetic field, there won't be any induced voltage. Again, so this expression is when you move it perpendicular to the magnetic field. Okay, so here's how you figure out this magnetic field. What happens is when you move this charge. Okay, so think of metals have free electrons. So when the electron is moving in this direction, V cross B. So here's the velocity of the and V cross B would be a vector. A positive charge would feel a force in that direction, and a negative charge feels a force in this direction. So when you move the rod, electrons will collect at the bottom, and so this end becomes positive. Okay, so here's the magnetic force, and now once there's an electric field established, the electric field is exerting a force on electrons in that direction. When that force balances this force, no more electrons will move there. Okay, so that determines the voltage you develop. All right, again, you take a metal rod, you move it in a magnetic field, in the presence of a magnetic field, and you develop a voltage across this metal rod. It's become a battery. Okay, so the energy you put in moving the rod is converted to electrical energy. Okay, so so when moving the conductor in the presence of magnetic field, the induced voltage is equal to the rate of change of flux through the loop. So for instance, when you move this rod as part of the circuit, as you're moving it to the right, the flux through this circuit is increasing. And Mr. Faraday told us that the induced EMF is rate of change of flux. Anytime the flux changes through a loop, that's equal to the induced EMF. So this induced EMF can be, if you imagine this as part of a circuit, the induced EMF is equal to that. Okay, so there's the flux. Flux is the magnetic field is constant, and the area of the loop is this length times the x coordinate. Okay, and the only thing that's changing is x. Okay, so dx by dt is v. Okay, so again, this moving rod is acting like a battery, and the EMF of the battery is BLV. Okay. All right, so now what we have done is we've seen two aspects of induced EMF, which is the result of this equation and this equation. Okay. And we've seen either moving a conductor in a constant magnetic field or a time-varying magnetic field producing electric fields. Okay. And you can use that electric field to drive currents in conductors. Okay. All right. So again, moving this conductor in the magnetic field made this act like a battery, and the voltage of the battery was BLV. Okay. Okay. So what this slide tells you is the following: because of the induced current. So when you move this thing, there was a current induced in the wire, and this wire feels a magnetic force in that direction. And so you had to keep applying a force to keep it moving. Because soon as the current flows, the conductor feels a magnetic force in the opposite direction. Okay, so to keep it moving, you have to keep applying a force. So whatever work you put in is converted to electrical energy. Okay, it's like when I lift a cup up, the work I did, what did it get converted to? Gravitational potential energy. Okay. Okay, so work you put in got converted to electrical energy. Okay, work done by the applied force is converted to electrical energy. Okay. Soon as you stop applying a force, this thing will stop. The rod will stop. Lenz's law tells you the direction of the current. If you move the rod in this direction, the current is in like that. And if you move the rod in this direction, the current is clockwise. Yeah. All right. So again, you take a rod and move it perpendicular to the magnetic field. The rod acts like a battery. Okay, they tested this using the space shuttle. Okay, so you guys know that the Earth has a magnetic field. So there's the North Pole, here's the South Pole. So here's the magnetic field, okay? And so the space shuttle was flying around the Earth like that. And so the space shuttle, this is the shuttle and there's the satellite. Okay. So there's the space shuttle and there's the satellite. So this wire was cutting the Earth's magnetic field, moving perpendicular to the Earth's magnetic field. This wire was 20 kilometers long. Okay, and the Earth's magnetic field is, I don't know at that height. Let's say it's about 0.1 times 10 to the minus 4 Tesla. Okay. Oh, there you go. 5 times 10 to the minus 5 Tesla. And the shuttle was moving at 8 kilometers a second. So the voltage that would develop across the wire would be 8,000 volts. And so they actually measured it, and it came out to 3,500 volts, because some of the charge would leak out. Okay, so this was interesting enough to test it with the space shuttle. All right, so now we saw that this equation tells you that changing time-varying magnetic fields produce electric fields. Okay. It turns out that we said that the nature of this electric field is slightly different than the one produced by a charge. Okay, so here's a electric field produced by this positive charge. Okay, and so this is the electric field produced by this charge, and the electric field produced by this guy is like this. So if the magnetic field is into the plane of the paper, this electric field is like that. So if the field is increasing in this direction into the paper, the electric field induced is like this. Well, what is the difference between this field and this field? The field between the curl for this is non-zero. The curl for this is zero. What that means is the following. If you take a line integral of this electric field, this is zero. For this electric field, this is zero. For this electric field, that's not zero. Okay, So this is known as a conservative electric field. This is a non-conservative electric field. Okay. Okay, so electrostatic electric fields are conservative fields. The line integral on a closed loop is 0. For this guy, the line integral is not 0. Okay? And that's what we mean by a non-conservative electric field. All right, now we'll look at some applications. Okay, again, Faraday's law says induced EMF is equal to time rate of change of magnetic flux through a loop, which is minus d by dt B A cosine theta. Okay, now we'll look at how to induce EMF. And like I said, you could change the magnetic field, which is hard to do. You could change the area, which is hard to do in practice. The best thing to do is change the angle between the area vector and the magnetic field vector. Okay, so here is the, in this diagram. Okay, I'll draw, here's B and okay, so the easiest thing to do is turn this loop of wire and change the angle theta. Okay, so make theta a function of time. So that's what we do in most applications. So in an electrical generator, what you have is a strong permanent magnet. Okay, so that's what you have at the bottom of the dam. And you turn this loop of wire by the flowing water, or in various devices, you move the water with you move this wire with appropriate technology. So the generators that you buy at home, the gas run generators, what do the gas motor is turning this wire, okay, which is producing the electricity. Okay, so in a windmill, the wind is turning this wire. In a dam, flowing water is turning this wire. In a coal power plant, you produce steam by burning the coal, and the steam is turning the wire. In a nuclear power plant, again, split nuclei produce steam, and that's turning the wire. Okay? So that's how you're producing electricity. Okay, you get an AC voltage when the wire is connected to the outside with these two slip rings. If you connect it using one slip ring, then you get a DC voltage. Okay. Now, omega is the angular frequency, and the maximum voltage, the amplitude of this voltage is N. N is the number of turns of wire. A is the area contained. B is the magnetic field strength, and omega is the angular speed. All right, so here's a fun toy. Okay, so you can take a loop of wire like this, and here's a ring. Okay, when you close this switch, this ring will fly up. And we can make a light enough ring, fly the height of that stairwell. So how does that happen? Okay, when you close the switch, you have a current flowing through this, and so which produces a magnetic field. And the magnetic field went from 0 to a maximum value. That changed the flux through this thing, and that induced a current. And so this becomes a magnet, and an induced magnetic field has opposite polarity. So for a brief second, you have a repulsive force, and this thing will fly up. Okay. Do you guys know what this is? You guys have seen this in your bathrooms or your garage? Yeah. What does this thing do?
Makes you so you can't chop yourself.
What that?
Makes it so you can't chop yourself.
Shuts off the power.
What? What then?
Shuts off the power or something.
Right. All right. So the idea is the following. So let's say here's a hair dryer. Let's say one of the wire frays, and then, or you drop it in the water or whatever. The wire frays, the wire hits the body, and then if you're holding on to it, the current goes through you rather than through the wire. And you don't want that happening. You don't want current flowing through your body. Okay. So let's see how what this thing does. Okay. So you have current flowing in, and how much current do you want flowing back in? Exactly the same amount. Okay. You don't want the current flowing through any other path. All right. So let's say this current is flowing through here. Stick your thumb out in the direction of this current, and it's producing a magnetic field like that. If there's an equal and opposite current flowing through here, there's an equal and opposite magnetic field through there. Now, what is the net magnetic field through this coil? Zero. The instant these two currents are not not equal, this magnetic field is not zero. Yeah. And so now you didn't have a current, you didn't have a magnetic field, and the instant the currents are not equal, there's a magnetic field induced, there's a current induced, and that'll shut off the device. Okay, and this thing can act within a millisecond. Okay, so that's what these things are. So if current leakage occurs, the flux through the sensing coil is no longer zero, and the induced voltage triggers a circuit breaker within milliseconds.
So then are you still shocked for like a really small amount of time before it?
Yeah, it's like you take a hot plate and put your hand there, that burned. Did that burn? Yeah. So it's the total amount of energy that matters. All right, so again, this Faraday's law is very important. You use it in many applications. All right, in musical instruments, so in a guitar, for instance, the string vibrates, except that and it produces sound, except that sound is very feeble. So in an acoustic guitar, the air box amplifies that sound. You have to figure out some way of amplifying that sound. Okay, so here is how an electric guitar does. In an electric guitar, you magnetize this portion of the string, and as the string vibrates, the magnet is moving back and forth. As soon as you have a magnet moving, you know what to do with it. You just put a coil around here. This magnet moving changes the magnetic field through there. That will induce a current in this wire, in the sensing coil. And once you have a current, then you feed it to an amplifier and feed it to a speaker. Yep.
So are all those little circles underneath the springs where underneath the strings where the sound hole would be on an acoustic guitar, all those little metal circles, are those the magnets?
These guys?
Yeah.
Uh,
Or is it at the bridge?
I don't know where the sensing coils are. I don't know. I just know the physics of it. All right. So did you guys understand that? And again, this is now you understand how a microphone works. Imagine this is a diaphragm. You attach a little magnet to it. You speak into it. Make the diaphragm vibrate, and there's the sensing coil in the back. Okay. So, okay. So, what I want you guys to remember for the rest of your life is, soon as you have changing magnetic fields, all you need is a sensing coil. Turn that motion into an electrical signal. And once you have an electrical signal, it's very easy to manipulate it. Okay? You can do all kinds of stuff with it. So, when a guitar string vibrates, its magnetized portion induces an EMF in the pickup coil. Okay, this is a soft magnet just to um, enhance the signal. Okay, so this is just a toy, but this will show you an important application. Okay, so here's a magnet, and here's a pendulum. This is a metal plate. Okay, and if you make this pendulum swing, what happens is, if it was not present between a magnet, this pendulum would swing forever. Okay. Now you take the same guy and put it between magnets. What happens is, as it's swinging through the magnet, a current is induced, and the current is induced such that it's of opposite polarity as this guy, and so this will attract it. If it's trying to swing away, the magnet will attract it and pull it back, and if it's swinging that way, again, it's attracting it and pulling it back. Okay, so if you swing it between magnets, this will dampen the oscillation. Okay, and it'll stop very fast. So eddy currents are such that they dampen the plate's motion, converting mechanical energy to heat. Okay. Okay. So what you can do with that is the following. So let's say you have a train, and you want to stop a train. Where is that coil? Okay, it doesn't show the coil. Anyway, oh, maybe that's the coil. So what you do is, when you want to stop the train, all you do is flip a switch, pass a current through this thing. Now this has become an electromagnet, and as it's moving, it induces a current in the rails. And the induced current is such that, so if the train is moving that way, the induced current there is, it's a south pole which is repelling it, and this one is a north pole which is attracting it. So the induced current, the current ahead is pushing it back, the current behind is pulling it back. So you get a very smooth and fast stop with this electromagnetic braking. And what is the other advantage?
No wear on brake pads.
No wear on brake pads. Okay, so this is guaranteed stop. All you have to do is flip a switch. Okay. So this is electromagnetic braking. You guys know how metal detectors work? All right, so these metal detectors so here's an AC loop. So when the current is flowing this way, it's producing a magnetic field like that, and when the current is flowing in the opposite direction, the magnetic field is like that. Okay, so this AC current produces a magnetic field that is changing, and the changing magnetic field induces a current in the receiving coil. Now, the instant a piece of metal comes in, this is producing an opposing magnetic field, and so now through the receiving coil, the magnetic field is smaller. So the current in the receiving coil drops as soon as there's a metal piece that intervenes. Okay, so that's how a metal detector works.
Wouldn't the metal have to be inside the metal detector?
Hmm?
How does it work when the metals, like if you have just a metal detector on a stick with a plate on the coils outside of, it's
Oh.
between like a receiving coil and
So this is how the airport metal detector works, and yeah. Okay, so so the Beachcombers one, it probably works like this. Okay. So here's an AC current, here's the receiving coil, and if the metal is outside, again, it's producing a opposing thing, which reduces the magnetic field in the sensing coil. Doesn't matter whether it's inside or outside. Yeah. Except that this is much more sensitive than this guy. All right, guys. So this ends this chapter.